So my project is about human detection in the traffic scene. The state-of-art pedestrian detectors all perform a single detection task, which only differentiates humans from background, i.e. the non-humans. So we proposed a detector named MTCN that can execute a multi-scale detection task, which can not only detect human beings, but also 6 common background objects in the traffic scene. They are the sky, road, trees, buildings, vehicles, and traffic lights. And by evaluation, our model achieves a significant detection accuracy improvement with the log average miss rate deduction of 4.43%. Pedestrian detection is one of the most practical and popular research topics in modern engineering, thanks to its direct applications in robotics, surveillance, and automobile safety. The detection has 2 stages. First, at the first stage, it extracts features from the inputs, and then they represent the feature in the vector form to do the binary classification into humans or non-humans. There are 2 approaches to the pedestrian detection. The traditional one uses hand-designed features, which include hog, varlets, and LBP, while the deep model while in the deep model, the features are actually learned all the way from raw pixels of inputs by multi-layers, and thus deep model has usually has a better accuracy performance than traditional one, since the features are specific and very input oriented, which makes the classification more accurate. One of the instances of traditional recognition is ACF detector, and one of the deep model example is CNN, as CNN will be introduced later in the background. So the insight of our project is that many of the mistakenly detected patches by a detector actually contain part of a specific background object. For example, we run the ACF detector with the Caltech dataset, and we noticed that except the correctly detected human patches in part A, they're actually they are actually and among the wrongly detected patches, many of them actually, in this case, you can see this patch actually captures the background object tree. This captures a vehicle, the car. This captures the traffic light. So in this project, we performed a series of tasks as listed here. First of all, of course, we propose a novel detection model, MTCNN, to detect both pedestrians and 6 common objects in the traffic scene. And then we collected the data set for MTCNN from the existing data sets, Caltech dataset, and the Cambridge dataset. And then we trained the MTCNN using the Deep Learning Toolbox Cafe. And then we evaluate our model with some other detectors to compare the results, the performance. CNN is convolutional neural network. It was first introduced by Chen in the early 90s, and it has, at the early stage, it has already delivered outstanding performances for the handwritten digital detection and human face detection. Recently, it becomes popular again. It's because um, is because of the nowadays the availability of large amounts of data set and the powerful GPU implementation that makes the training of large models possible. Caltech dataset and Cambridge dataset both records 3 scene images. The difference between those two, the main difference is that Caltech only annotates the humans in the images with the location information, while Cambridge dataset, every pixel in every frame is annotated with a RGB value. As you can see here, the example, the human is actually labeled blue, and the building is red, and the tree is kind of brown. So the design of our project actually contains 2 parts. First of all, we need to obtain the training data set for MTCNN, and then we need to train the proposed detector MTCNN. The training data set for MTCNN actually consists of 2 parts. One part from the human patches and the generic background patches that obtained from running ACF detector with the Caltech dataset. We should notice that here the background patches are non-labeled, since Caltech dataset only the humans in the images are annotated, and then we transfer the 6 kind of labeled background data from Canvas dataset using the following method, and we can avoid intensively time-consuming manual annotation of the background scenes. So first of all, we run the ACF detector with Canvas dataset, and then among the output bounding boxes, if inside a bounding box over 70% of the pixels belong to the same object. For example, if it belongs to the sky, then the patch will be regarded as the sky. And then we adjust the detection threshold to make sure there are over 5,000 patches of each kind. And then we select top 5,000 patches of each kind according to the detection scores given by the ACF detector. So MTCNN basically follows the standard CNN, which consists of 4 convolutional layers and 3 pooling layers and 2 fully connected layers. And at the output layer, it has the softmax classifier to classify the inputs into 7 objects, including humans, and here these 6 kinds of background objects. And between two convolutional layers, it has a operation flow like this. First of all, the output of the previous convolutional layer is convoluted with a filter, and then the output is passed to a linearity function, and then we do the max pooling and the normalization to get a feature map. If here Next, there's the next convolutional layer. Then the feature map here is actually back to the is again the output of the previous layer, i.e. The input to the next convolution layer. And here the same operation flow will be repeated again. So the training of MTCNN is conducted using a toolbox, deep learning toolbox called Cafe CNN. And the training, the main algorithm for MTCN training is called back propagation, which first computes the classification error using the closed entropy loss function. It compares the estimated labels at the upper layer with the annotated training labels, and then the difference produced is used to adjust the network parameters. The network parameters include filters at the convolutional layer and weight matrix at the two fully connected layers and the sum bias, while this kind of function gradient descent. And all the detectors on evaluation, all the detectors listed here are tested on a Caltech dataset. And here we have some three main results. First of all, MTCNN achieves a log average miss rate less than 30%. Compared with the CNN plus data, which is a single task CNN, but trained with the same data set as that of MTCN, i.e. the data set talked here. So it reduced the miss rate by 3.45%. And compared with the original CNN, which is trained just on a Caltech dataset, it reduced the miss rate by 4.43%, which is the main achievement of our project. And also we noticed that the traffic lights is actually the most confusing background object for pedestrian detection, since CN plus traffic light tasks, i.e. the binary task CN trained to detect both humans and traffic light. It has the lowest log average miss rate among the 6 binary task detectors, CN detectors, as you can see here. And here I want to expand what does the figure means. The false positives per image means on an image how many of the non-humans that are actually wrongly detected, mistakenly detected as humans. And the miss rate is from 0 to 100%. It means on an image, the percentage of the humans that has not been detected, and the log average miss rate means means the log average of this of a curve, which is just a number, as you can see here, just a number. I hope I made my presentation clear, and yeah, this is all. Thank you for your listening.